Hello, everybody. Let us start our discussion today. We're still in the process of connecting the geometry, differential geometry we have learned, to physics or general relativity or gravity in this case. And let us pick it up from where we left last time. We looked at deviations of trajectories in gravitational field, first using our good old well-known Newtonian mechanics, where, if you remember, that we had these trajectories, and in this case of Newtonian mechanics, they can be leveled by time. So time varies this way. And we said that we are looking at the deviation between the trajectories at the given time. So if this was my vector xl, this is xl plus the deviation which we called xi. And we looked at the question, we asked the question that how does this deviation changes with time, particularly the second derivative, which is like acceleration. And the acceleration changes with time as the second derivative of the potential phi, gravitational potential phi. Then we compared it with the similar situation in a case where I don't have any gravity as such, but I have trajectories in a curved manifold, can be curved manifold, or a Riemannian manifold, where again the trajectories in the Riemannian manifolds are geodesics. So these are so-called time-like trajectories, means that these are the trajectories of an observer or a particle. And as you can, if you can go jump onto the reference frame of the observer of the particle itself, the space part of the interval doesn't change, only the time part changes. So all the interval is there completely given by the proper time difference between any 2 points in the trajectory. That's why these are called time-like trajectories. And we parameterize this, we can parameterize this in terms of the proper time. We did a general parameterization called lambda. And then again, we can have many of these geodesics. And this way we called it some other parameter, say eta. And we looked at again the deviation vector. In this case, how do I if you remember how we defined the deviation vector, the deviation vector xi, say alpha, was defined as dx alpha d eta. And we asked again the question how the this deviation vector, second derivative of this deviation vector, changes, and we got this equation. And we found surprisingly that the acceleration in this case, if I call this acceleration, which is essentially second covariant derivative of psi, depends on the Riemann curvature tensor, apart from other things. So it seems that this quantity, the Riemann curvature tensor, and so this quantity phi lm is kind of equivalent to the quantity in case of the curved space. So remember, the curved space, there is no gravity as such, but we can have a Riemannian, general Riemannian manifold where there can be curvature. It's not necessarily a flat manifold. A flat manifold is one where, if you remember, all the components of the Riemann tensor is zero. But I can talk about a general manifold where the Riemann tensors has components. And then I can map such a manifold with the case of a particle moving in a non-uniform gravitational field. If the gravitational field is uniform, then it turns out that it corresponds to the case in the right hand side of the curved space where the manifold does not have any curvature. So it seems that gravity is related to the curvature of the manifold, Riemannian manifold, or the four-dimensional space-time that we are interested in terms of special or general relativity. So gravity seems not like a force, but more like a curvature of the space-time. What we'll try to do today, one cannot derive how one should write down gravity in terms of the curvature of space-time, but one can argue and write down a kind of principle saying that this is how I will describe gravity. In this case, remember, we are talking about trajectories in a region where, let us say that in this case, we are talking about trajectories where there is no mass or energy present. It's only that particle which is moving in the gravitational field, only that particle is present. There's no source of mass or energy. So we can think of today what we would like to do. We can think of writing down gravity in a case where this space-time is free of any mass of or energy. Now that is in the region of space-time where we are writing down gravity. It doesn't mean that everywhere in the space, in the whatever infinite space you can think of, there is no mass or no energy. It is just only in the region we are trying to write down. We don't have any mass or energy. In that case, what can be the description of the gravitational field in terms of the curvature of that manifold we call space-time is the question we are asking today. And again, as I said, I cannot derive it from any first principle because what we'll write down today will be the first principle. Maybe in the next lecture or the next to next lecture, we'll have an argument, a little more first argument to go to there, but you will see that that depends on another first principle. So really, we cannot derive the equation that I'm going to write down at the end of today's lecture, but you can speculate about it. Okay, so let us go ahead, and first what we'll do is we'll look at one such trajectory in Newtonian mechanics and then in terms of the trajectory in the curved space, which is the geodesic, and try to map one to the other and try to see what we get in terms of the potential or what replaces the potential. Let's start doing that. So this is, we are considering motion of a massive particle in a weak gravitational field. So what do I mean by a weak gravitational field first? First thing I will say that weak, the meaning of the weak we are trying to describe, we say that the gravitational acceleration, so if a particle is in motion, and in this case it's a freely falling particle, so let me also put in that particle is freely falling. So there is no other force. There is a gravity, and as we have learned in the principle of equivalence, that disappears if the particle is freely falling. So in such a case, what we will have ensured is that The acceleration due to gravity, if the particle is freely falling, it will gain speed, as we know in Newtonian mechanics, cannot make the speed of the particle anywhere near to c. So this particle is moving with a moderately small speed, which means in term that from any reference frame that we'll talk about, beta, which is, if you remember, we write beta for v by c in special relativity, that is 1, and gamma is also 1. I'm sorry, beta tends to 0 and gamma is 1. This tends to 0, and gamma, which is 1 by 2 to the power 1 minus beta square, this tends to 1. All right, so this is the first case, first thing. The second thing is that what is the gravity supposed to do? Well, if there is no gravity and no source anywhere in the world, we know that we should maintain special relativity. So the metric that we get for special relativity, the metric will get modified because of there is a gravitational field, but it will get modified very little. So I can write the metric in this case is just a first order perturbation. To this special theory of relativity metric, which if we write in terms of equations, so g alpha beta, the components of the metric that we will deal with, is eta alpha beta, which is diagonal 1, minus 1, minus 1, minus 1, plus a small change h alpha beta. And we say that the gravitational field is static. Well, if you go to a reference frame, you can make it become a function of time in an arbitrary reference frame, though if it is not a function of time in one reference frame. But because we are saying that the beta is tends to 0, etc., etc., this is a fairly good assumption to say that h alpha beta is not a function of the time coordinate. So these are a function of only the spatial coordinates, which I write as xl. So this, let me remind you, all the spatial coordinates. Okay, so this is the setup in which we will try to find the trajectory of a particle, and in using Newtonian framework, and then using uh, the motion in a curved space-time. So that will be essentially it's geodesic. So in Newtonian gravity, the gravitational potential, if I write phi, and this is a function of the spatial coordinates only, then equation of motion this will be, let's see. So it's the second derivative of the radius vector d2xl if I write, and this is minus del L phi. If you wish, you can write it this way. So this is essentially the result that you know. This is the equation if you have Newtonian gravity. So this, if I write it a little bit more, okay. So del m phi is the gradient of phi. Fine. So let's one line to write the Newtonian gravity. Let's move to the curved spacetime. The equation is that of the geodesic, and you see, we said that the velocity is v by c, and the gamma is almost always 1. Now in curved spacetime, so first of all, let me write down the velocity, the velocity for vector, which is u alpha, and let me remind you that this is c gamma, and then if I write vl gamma, where gamma is our good old gamma, and c is the speed of light, and vl are the components of the velocities, the three velocities essentially. So vl is dxl dt. This t is the coordinate time. It's not tau, which is the uh, proper time. And you may also remember that the gamma is given by dt by d tau. dt by d tau is nothing but gamma, and that is 1, which essentially means that this can be approximated to c and vl, and as c does not change, du alpha dt or du alpha d tau will be 0 for alpha equals to 0, which means that if I write now geodesic equations, let me write the geodesic equations, all the equations first for you, and then we will write down the specific ones. So this d2x alpha d tau 2 plus this is alpha, say beta gamma. Okay, I will not use beta and gamma because they are already used. So say mu nu, u mu, u nu. This is my geodesic equation. And let us break it down into space part and time part. This I can also write as du0, the time part I can write this way, plus gamma 0 mu nu u mu u nu equals 0. But you see that du0, u0 being only c to the first approximation, that doesn't change with anything. So this I can simply write as du0 d tau equals 0. Right hand side has to be 0. This gamma thing has to be 0 for this to satisfy. What about the spatial components? So this is the time part. Spatial parts are the ones which are interesting because those we can compare with what we have from the Newtonian gravity. So this is d2xl d tau 2 plus gamma L, and what can I write here? So let's see. I can write here. So this is let me write first. So this is u 0, and then I will get u 0, and I can have them as the spatial components. Okay. Obviously, I can also have this type of things. This is the all the geodesic equations, the entire geodesic equation. Now you see that we said that we are moving in non-relativistic speed, which means that all our velocities are much lesser than c. V by c tends to 0, which essentially means that these VLs are much lesser than c. So these components are all very small compared to what I have here, which is essentially c squared. So this I can approximate to. So this will become, only the first term will survive. U0 is just c square, U0 square, and I can write a gamma, but that's 1. So this equals to 0. And you remember that d tau is just dt, because dt by d tau is 1. Dt by d tau is gamma, which is 1. So dt is equals d tau. So I can do a further approximation to write this as d2xl dt2 plus gamma L00 c square equals 0. So this comes from curved space, and the Newtonian expression is quite similar. It's phi equals 0. So we see that I can now compare this and this, and probably will be able to guess what at least some components of the metric is. So let us try to do that. To do that, what we will do is we will write gamma L00 and try to figure out what is gamma L00 in terms of the metric. Okay, so let us calculate gamma L00 in terms of the metric. This is half G L, and I can have anything as mu. Mu can go from, remember that this can go 0, 1, 2, 3. This can go 0. I'm sorry, 1, 2, 3 only. This is spatial. This is all space time. Okay, so I have two G's here as plus and one G as minus. This last one will be G00 comma mu. And here it will be Z0 mu comma 0, and again mu 0 comma 0, which is same as G0 mu comma 0. But remember that our metric is only a function of the spatial coordinates. It's not a function of the time coordinates. So these derivatives goes to 0. And here the only derivative that is possible is in terms of the time coordinates. Sorry, yeah, in terms of the spatial coordinates, not time coordinates. So I can write gamma L00 as minus half G L, and let me write this first, then it will be clear. So this can only be spatial components. So I write M here, which goes from 1 to 3. So this is only M. All right. Now remember that we wrote the the metric as first order perturbation from the metric with the str. So this essentially is eta Lm, and you can calculate for the first order perturbation the h term, the perturb term will be negative here, and this times eta 00 plus h 00 derivative with respect to m. Now eta 00 is constant, so the derivative with respect to m for that is 0. So I get only minus half eta Lm minus h Lm and then h 00m. And if we want to keep only first order terms in first order in h, this term is second order in h, so I get half minus half. Eta Lm is nothing but 1, and the only place where it is 1 is where m equals to L, so this is nothing but h00 L. But just to keep the sanity of the symbols, I will write this as of eta Lm. Okay, so m is summed over. h00 is just a function. All right, now let us compare. Let us see what we have got. We have a derivative with respect to L here. So we have a derivative with respect to L essentially here once this m has to become L. So you can see this and this, if I compare, I see that minus half eta Lm h00m times c square is phi comma L. So h00 then up to a constant, h00 up to a constant is nothing but, so there is a minus here also, is nothing but phi by 2 phi by c square. I should have added a constant here, but you see, you already know that the constant is 0. Because if the constant is anything other than 0, then your metric, so let's write the constant. So let's say it's a constant. Then you see the g00 term of the metric becomes 1 plus constant plus 2 phi by c square. Well, that cannot be true unless the constant is 0, because g00 and there is no phi should be 1, the str metric. So the constant is 0, and there you get that in case of weak gravitational field, if I compare both of these, we get hence, so let me write it here clearly, in weak gravitational field, Newtonian limit g00 is 1 plus 2 phi by c square. This we have got. Remember, phi is the phi that you get out of Newton's gravity. Once I get this, let us now try to apply this to a case with which we started our discussion in general relativity, which is the Pound and Rebecca experiment. And now we will be able to see it in terms of general relativity because we have worked this out. What is G00? We'll see shortly how. So let's see what was the experiment. In the experiment, we have a tower of height h, and because of that, the gravity is different at the top of the tower compared to the bottom of the tower. Let's say bottom of the tower, the gravitational potential is 0. At the top of the tower, then I can say the gravitational potential, not the potential energy. The potential is minus gh because the potential decreases as you go to the as you go up. You have a clock here. In the original case, we said that we are sending a light signal from the top to the bottom. So we said that this is my z axis, this is ct because z is the vertical. Usually we consider z to be the vertical, and the space-time diagram is not correct, that we know already. So this is the world line of an observer sitting here or standing here. So I call this A, and another observer here we call B. There are two different observers. Their world lines are like this. So this is z equals to 0. This is z equals to h. This observer is sending light signal to this observer at equal interval. So this interval I can call like delta t. And what we found, or what Pound and Rebecca found in their experiment, is that the interval here and the interval here doesn't match. They doesn't agree. So if I call it delta t prime, there was a certain difference between delta t and delta t prime. Now we want to understand this in terms of the perspective of general relativity. So first thing that we will try to do is to figure out that what will happen, how will I measure the proper time in case of general relativity. What we have already seen is that in these particular cases, G00 is given by 1 plus 2 phi by c square, and this will be of our importance today. We know that the interval in general is given as ds square. This is true for any coordinate system. This is the definition of the interval. What I do is, I now consider a freely falling observer. In the gravitational field we have here, and this freely falling observer has a clock So this clock will always measure the proper time interval. The observer is falling freely. Observer with respect to himself goes nowhere. So always for that observer, the interval is completely time-like separated. So he will measure the proper time with his clock. The question is, what about the observer standing here? Now for that observer, if I consider the moment the clock is very fast, this person doesn't move that much as he's falling freely. So they're almost at the same point. So for that observer, for observers in the position A, ds square is given by g00 at A, and how much time interval that observer sees between the two events that happens. The two events are the two consecutive clicks or ticks of the clock of this freely falling observer. These two events happens almost at the same time. The social separation I can forget about. So only the G00 component survives. And what is this equals to? So this is equals to, because this interval is same in all reference frames, so I can now go to the reference frame of the observer who is freely falling. So in his reference frame, the interval is just c square delta tau square. I should not write d, I should write d delta, because this is still a small finite time difference. So which means I can measure delta tau as 1 by c integral over that small time period. And again, I don't need to write an integral here because this is measured at A and root over of G00 at A. So this is what the difference in the two consecutive ticks, or I can say the proper time period of the clock. Now this is in the freely falling frame, and that is important because in the freely falling frame, according to the postulates of general relativity, particularly the equivalence principle, the freely falling frames are equivalent to a special relativistic frame, and in a special relativistic frame, all clocks run at the same rate. So delta tau, this means, will always be same, will be same in all reference frame. Everywhere. So now when I come to this person, when I come to the bottom of the tower and this person try to measure the time interval between the ticks as sent by the person A when he's near to the bottom, what will he measure? So they'll measure delta tau as 1 by c delta x0 now at B. This two will be exactly same, that is what it is claiming. G00 is different because phi is different at two places, at the top and the bottom of the tower, and G00 depends on phi. So because G00 is different, it is easy to see that delta x0 and delta x0 at A and B are different. And I can find out what is delta x0 A by delta x0 B now. This ratio is given by A is the source and B is the observer. So this is given by now what is delta x0? Delta x0 is the delta x0 by c is the time difference, which is the time or the time period measured by the person at A or the person at B on at fixed to the tower, this people measures this time difference. So for these people, these are the time periods of the clock, and the time periods are inverse of frequency. So I can say that they will see the light is coming with the frequency nu A here and nu B here. Okay, so I say light and clock kind of synonymously. What I mean is that when I have a wave, I can consider a clock made by the fact that the clock ticks when the wave has the maximum amplitude. So we are talking about the difference between these ticks. So this is time, this is amplitude. We are talking about difference between these consecutive ticks. So that also corresponds to the frequency, or that corresponds to the time period. Inverse of that is frequency. Now what is this? G00 at B is the phi at B is essentially 0. So G00B at is 1. So this is 1 by, and this is 1 minus GH. Now this G is the 2GH by C square. This G is the acceleration due to gravity, which approximates to 1 plus GH by C square. So we see that nu B equals nu A, the frequency at the top, into 1 plus GH by C square. This is exactly what Pond and Rebecca saw, the change in the frequency. So now we have an explanation of the Pond and Rebecca experiment in terms of the general relativistic framework. What we said here is that we have a clock, atomic clock, with the person falling freely from A to B. That person's clock always ticks at the same rate when he looks at the clock. But when it will be looked at by an observer at A and an observer at B who is not falling freely, so those observers are doing the experiments by staying at A and staying at B, so they have actually this type of trajectory. This line should have been vertical. So they will see difference in the frequency of the clocks. That completely explains the Pond and Rebecca experiment. We know that in Newtonian case, the geodesic deviation is given by this, and in curved spacetime, it is given by this. And there is a hint that there is a second rank tensor, because this entire thing is replaced in place of phi Lm. So that's a second rank tensor because mu and beta are contracted. So that second rank tensor is what that is supposed to give us the effect of gravity. It is clear from the geodesic deviation. You see, if phi Lm is 0, then of course I can go to a freely falling reference frame and the effect of gravity disappears. If phi Lm is not 0, that also means this second rank tensor with R, with Riemann curvature tensor, is the thing that is making us feel the effect of gravity. In matter-free space, the Newtonian gravity is given by the Laplace equation. or the Newtonian potential comes out as the solution of Laplace equation, which is grad square phi equals 0. So this is a second derivative in phi. Well, so this is the clue number 1. The clue number 2 is that we have already seen that phi comes in the metric. So we saw that G00 component has at least that component has phi. So phi comes in the metric. And another thing we see is that we have this thing u mu, u beta, u mu. Remember, this was replacing the second derivative of phi. So this is essentially replacing grad square phi in my Laplace equation. Now this quantity, I can manipulate this a little bit. What I can do is that I can manifestly show this as a second derivative, as a second rank tensor, by multiplying this with g, let's say beta mu and g alpha mu. What will this give me? So see, this quantity is dx mu dx beta g beta mu. Right? That's just ds square by d tau square, which is nothing but c square. So this quantity is just a c square. It's a constant. And this will make this a Ricci scalar. Sorry, Ricci tensor, which is a rank 2 tensor. Right? So that equation we had is essentially a kind of an equation with the Ricci tensor. So the Ricci tensor is taking part of the second derivative of phi. And phi have the metric. So we can say that effect of gravity would be manifested in a second rank tensor that have what the second rank tensor should have. The second rank tensor is kind of given by this type of r beta mu. So it should have the components of the metric, derivatives, first derivatives of the components of the metric, which comes in the Christoffel symbols, and the derivatives of the Christoffel symbols are also there in R. So the second derivative of the components of metric. And you see, it's all the derivatives of the metric, and we have seen that it's kind of smelling like the Ricci tensor. So this tensor will have, so it will be symmetric, so it will have 10 independent components. Because it's symmetric. and second rank, right? So such a tensor can be always written in terms of R alpha beta, which is the you can write it downstairs or upstairs. Let me write upstairs here. That will be clear why I write that way in next class. Then in terms of the Ricci scalar, see this is the tensor, second rank tensor itself, R alpha beta, which we had already. Then the Ricci scalar times G alpha beta. G alpha beta is also second rank tensor by itself. And it can also be just G alpha beta because these terms are there. So it will have a form which should be something, some combination of this. So once I know what is A and B, then I can figure it out what this should be. And you see the solution of this, what should be the solution of Laplace-like equation in GTR, what it should be? Well, Laplace equation solution is phi, which gives you G in the curved space. Here also it will be G, because see, it's going to be this is a differential equation in G. I mean, this is a differential expression in G. You have to make it an equation. So if you compare now, and I'm writing easiest choice. We'll discuss maybe in the next class why I call it easiest choice. Okay, actually, if I want to write exactly for Newtonian gravity, it is just G alpha beta equals 0. G alpha beta, if you remember, is the Einstein tensor, which you introduced last time, and you probably know now why it is called Einstein tensor. This is what Einstein found as the equation for the GTR. The lambda, we will discuss why I have written a plus lambda here. Comparing with Newtonian gravity, we get only this. So G alpha beta, which has capital R, Ricci tensor and Ricci scalar both, has second derivative of the metric. So it's an equation, it's a very complicated nonlinear second order differential equation on G alpha beta. G alpha beta has 10 components. Small g alpha beta metric has 10 components, independent components. Einstein tensor also has 10 independent components. So these are 10 equations to solve for those 10 independent components. Okay, so we'll stop here. At least we have come to some notion of JTR today. One has to remember that we cannot derive this equation because this is kind of the first principle. We have just argued to write this down, and I have even not showed you how from the Newtonian gravity you get this expression. How do you compare it in a full-fledged Newtonian gravity, not only in very big field like where you can write it as mgh. You compare it with the point mass case and then you can write it down this way. That's it for today. We'll take it out from here in the next class. Thank you.